Welcome back, guys. Tonight we're going to talk about arcs and chords. So we're still talking about circles. We're just going to add in a couple of extra little pieces. To start off, we're going to do some vocabulary. Our first two vocab words, we have arc and we have semicircle. So an arc, like it says here, it's just part of a circle between 2 points. So if you take from D to C, that's an arc. If you go along the circle, or from B to A, or from D to B. All of those are examples of arcs. They are measured in degrees. Just like an angle, they have a degree measurement. So like from D to A, we call that a semicircle because it's half the circle. And as we know, circles have 360 degrees. So a semicircle would have to have half that, or 180. So arc DA is 180 degrees. Now, we do run into a problem here where if I say arc DA, you don't really know which arc DA I'm talking about. Are you talking about the top half of the circle or the bottom half of the circle? Now, with semicircles, it doesn't matter that much because they're going to be the same measure. But it is sometimes important to be able to differentiate between them. So in order to talk about this top half of the circle, instead of just calling it arc DA, I'm going to call it arc DCA. And because I'm going to D to A, but I'm going through C along the way. Or DBA, either one of those works. I just have to pick some point that's in between them and tell me that. If I want to talk about the bottom half of the circle, that's kind of hard. In order to do that, I'd have to have an extra point in there, and I could put one in, but since I don't have one, I don't really have a way to refer to it. So, moving on. Same picture, talking about central angles. So each one of these arcs has an angle that is central to it. So it's called central angle because it's at the center, is where the vertex is. So if you look at the formal definition, it's formed by two radii. There's always an arc that results from it that goes along with it. So for instance, angle CEB would be a central angle because E is a vertex and it's the center of the circle. To go back to arcs a little bit, we do have two additional types of arcs. So if you go with central angle CEB, that arc there that's formed, arc CB, that's a minor arc because it's less than half the circle. It's a small arc. As opposed to a major arc would be if we wanted to talk about more than half the circle. The issue is that when you're naming these things, if I said arc CB, well, you'd assume that that's the arc between C and B, this little bitty guy up here. And if I wanted to talk about the major arc, the one that goes from C to B the long way around, well, I have to have some other way to talk about it. So what we do, just like with semicircles, we use 3 points. So we say it's not arc CB, that's the minor one. If we want to talk about the major arc, it would be CDB or CAB. We have to have that extra point to say that we're going extra far. Major arcs always have 3 points to them. Minor arcs, you can have 3 points, but you only really have to have 2. Two more vocab words on the arcs. Adjacent arcs, adjacent, just like everything else we've used, adjacent always means next to. So anytime you have two arcs that are next to each other, so like arc DC and arc CB are adjacent arcs. And then congruent arcs are exactly what it sounds like, arcs that are the same size, the same number of degrees. So two 60-degree arcs would both be congruent arcs. Okay. Now on to our theorems and postulates. Our first postulate of the evening says that if an arc is composed of adjacent arcs, so like for instance we have AB and BC, if you put them together we get arc AC all the way around. If we do that, all we have to do to get the total arc is to add up the sum of the components. So if you want arc AC, it's just AB plus BC. You just add those up. So if we said that AB here was 80 degrees, and BC was 20, then you get 100 degrees total. So just like we would do with angles, same thing. It's just arcs this time. The next theorem is slightly more complicated just because there's a lot of words here. But really all it says is that if you have two angles or arcs or chords in a circle that are congruent to each other, and it works with congruent circles too, but if you have in the same circle and they're congruent to each other, they all kind of come in sets. So you get a central angle and a chord and arc that all are kind of formed together. So like right here you get this grouping here, angle EAD, chord ED, and arc ED kind of all go together. And if any one of them we can say is congruent to the set over here, we have angle CAB, arc CB, and chord CB. If any one of them is congruent, then the other ones are too. They kind of come in sets, is what this theorem is talking about. So I like to call it the central angle chord and arc set theorem. Two more theorems. These ones are going to deal with chords with a radius that's intersecting them. So if you look here, we have a chord EF, and we have a radius CD, and we know, based on this little box guy here, that we have perpendicular lines. So the theorem says that if a radius is perpendicular to a chord, then that radius is also bisecting the chord. So that means that CD is bisecting EF. It's cutting it in half. And anytime you have that nice little perpendicular radius, it bisects the chord. Last theorem of the evening, perpendicular bisector means radius theorem. Kind of reverse, but not quite, because since we can't really talk about a radius for this, I'm going to use the word diameter instead. But it's basically the same thing. It says that if we have a chord, in this case JK, that is a perpendicular bisector of another chord, so JK is perpendicular and bisects GH, so we see the little box there and the two congruent segments, so it's perpendicular and it bisects it. If you have that, then JK must be a diameter. And we know that GH isn't because we can see that, but also because it's not bisecting JK. JK is the bisector, so it must be the diameter. Okay, a couple of quick examples. First one here, we got these two circles, circle A, circle B, and we're given that they're congruent circles and that they have a congruent chord, which means, if you look back at our set theorem, it means that CD, the arc, has to be congruent to EF, the arc, and those 25y degrees and 30y minus 20 degrees. So I'm just going to kind of say that those arcs have to be congruent. That's my central angle chord and arc theorem. I plug in the values for the two arcs, so 25y equals 30y minus 20. Start solving. I'm going to subtract 30y from both sides so that I get only y's on one side. So I get the negative 5y equals negative 20. And then I divide both sides by negative 5. Remember, a negative divided by negative is a positive, so negative 20 divided by negative 5 gives you 4. So I end up with a y equals 4. And then I can just plug that back in and find that CD is 25 times 4, or 100. So that should be the same as EF. So just to double check myself, I'm going to go ahead and do that. 30 times 4, that's 120. Minus 20 is 100, so it did give me the same thing, so that's good. I got 100 either way. So the answer is the measure of arc CD is 100 degrees. Second problem. So once again, we have arcs and chords. I'm told that chord JK and chord LM are congruent to each other, which means that their corresponding arcs have to be congruent as well. And so I say that the arc JK is equal to arc LM, and that's my little central angle chord and arc set theorem. And then I'm going to plug in my measures. It's a little tricky here because if you look at JK, it's got L kind of stuck in the middle of it. So what I'm going to do is I'm going to use that arc addition postulate. I'm going to say that 4y plus y, or 5y, is going to be JK. So I got a 5y there, and then on the other side I got the y plus the 68. So I end up with 5y equals y plus 68. Start solving that. Subtract y from both sides. I get 4y equals 68. And then I divide both sides by 4, so y is 17. And I end up with that 17, and then I just stick it back in for JK, which is what it was asking me for. So JK, remember, was 4y plus the extra y there, so 5y's. So 4 times 17 plus an extra 17, or 5 times 17, either way you want to go, you end up with 85 as the answer. And that's it. Hope you guys enjoyed it. See you guys in class tomorrow.